my name is Julius Höhne, and I'm the sales manager of Dualis together with my colleague Evelyn Dietrich. I'm responsible for factory simulation and especially for the simulation tool Visual Components. Yes, and today I want to take you on the journey from concept to reality. And imagine you are able to design and test and optimize an entire product line even before you have built or bought just a single physical part. And that is what we do with Visual Components. And today I want to demonstrate a little bit how simulation tools like Visual Components works and how it allows you to visualize a product line from the very first idea to a digital shadow of an existing production line. At every start of the process, from developing a machine to having it running on the shop floor, there's always the idea. And with Visual Components, you are able to transform that idea into a working 3D layout, into a moving 3D drawing. That means you can quickly build complete factory setups, including feeders, conveyors, robots, machines, human workers, HEVs, and much more. And that brings you into the situation that you can do some tests like robot accessibility or capacity utilization of machines or HEVs or human resources. In a simulation, you can play with these properties and you can add a resource like a human, or you can add a HEV, or you can reduce it. And then you can find out what happens if you do this. And so you can do different tests and evaluate if a system works before you have to take a decision. And you also can create pictures and movies of your idea that helps you to present your idea to your colleagues or to your customers. And here you can see a digital model. It's a digital model of producing milk cartons and filling milk cartons. It's a milk carton packaging line. And you see here, you see the arrows. The light blue arrows here, they represent the material flow of the milk carton itself. Here in that machines, the milk cartons will be filled and closed, and then they come on the conveyor, move up to that point here, and here the milk cartons will be packed into a packaging carton. And the packaging carton comes from here. That will be represented by the red arrows. And here, like I said, the milk cartons comes into the packaging carton. And now you see there is a dependency between the milk and the transport carton. The transport carton can only move forwards once enough milk cartons have been arrived. And on the other hand, we need enough transport boxes to package all milk cartons and to avoid material jam on the conveyor. And then in the next step of this model, the packaging cartons will be closed. That happens here. And a robot will stack the transport cartons on a pallet, and the pallet will be packed with foil. The stacking on the pallet happens here, and here the whole pallet will be packed in foil. And in the end, the forklifter here that has the target or the task to fill the process with Euro pallets and bring the packed pallets back to a truck. And all this information about the goods flow and what needs to be available at which time is implemented in this simulation. So the simulation is a self-regulating model of a production line. So in this video, you can see how to create a digital model. We just placed the machines and the conveyors in the 3D world. And that is one benefit of a program like Visual Components. It has an e-catalog which includes nearly 4,000 items, such as machines, conveyors, robots, safety fences, industrial trucks, human workers or AGVs, and much more. And you just need to place the items in the 3D world, and the connection between the individual components, like from one conveyor to the next, that happens automatic. So no programming skills are required to create a simulation like this. And everything you see here is based on a plug-and-play solution that can be set up quickly and easily. So this makes it possible to turn an idea into a comprehensible model in a very short time. So these models can already be used for presentations internally within your company, or for sure with your customers, to demonstrate how the requested solution from your customer, how you want to solve this problem. And in addition to that you have this digital model, you not only have moving pictures like a visual representation of how the goods flow will be. The digital model allows us much more. It allows us to identify bottlenecks and draw conclusions about resource utilizations. We have analyzing tools, and we are able to extract detailed information over extended periods, like, let's say, like the robot status. How well is the robot utilized, and when do a storage area reaches full capacity, or is the forklift fast enough? Does the robot move fast enough? Do we have enough pallets available in the process? And we can report these KPIs like OEE and OLE, and we can already evaluate how long it takes from the moment a milk carton is filled to the moment it is packed and loaded onto a truck. And that gives us a perfect basis for optimization of the layout, and in the end, for decision making. And in my opinion, simulation tools are not just tools for engineers. Also, sales manager can use these tools to give clear, easy to understand presentations, and as a result, more transparent and convincing proposals, which helps you to argument how you will solve customers' problem. And once you finish the layout design, the feasibility checks, and the process validation, our digital model has accompanied us from the initial idea of a production line through internal presentations, through customer presentations, through the quotation phase, and all the way to the optimization of the overall concept. And now we know exactly where each element of the production line in the 3D world has to be and has to be placed, and what cycle time is required. We understand how many workers we need, how many forklifts or AGVs are needed, and we could even provide already an estimation of energy consumption. And once all these data leads into a final decision and our customer has placed the order, the digital model starts to transform into a digital shadow. Because after the customer has placed the order, the digital model helps the engineers to design the parts for the system, or the buyers to buy conveyors, and because everything is already defined. And once the parts are ordered and produced, and in the end, the machine and the production line is assembled to a physical production line, the PLC programmer can start to test the program. And beside this process, the PLC programmers start to develop the control software. And that based on the simulation on 3D drawings and circuit diagrams. And traditionally, these three PLC programs can be tested once the system is physically assembled. And with our digital model, we have a significant advantage because we can virtually test the program in advance before the physical setup begins. And this saves time, it reduces risks, and significantly improves the quality of the commissioning. Because here you see, before the PLC programmer works directly on the physical system, they can test their program by using the digital model, and therefore they just need to connect the programmer's software with a simulation, and then we can exchange the signals bidirectionally. And at this point, the simulation is no longer a self-regulated model with a predefined behavior. It becomes driven by the actual logic of this PLC program. And so our digital model transformed from the digital model to a digital twin. The digital twin sends the real signals to the controller, which evaluates the system states and returns corresponding signals back to the simulation. For example, these conveyors you can see here can now be switched on and off directly by the PLC program without requiring a physical system. Major benefits for this, we increase the safety. Dangerous situations can be identified here in this virtual environment, and we can handle this in advance in the PLC logic long before the physical machine is powered on. And this helps to prevent damages to the equipment and ensures that people working nearby the physical machine during the commissioning process are not put at a risk. And another advantage of virtual commissioning is the considerable time saving in office. Traditionally, the process follows the sequence. We plan the system, we buy the components, we manufacture it, and then we assemble. And only after that, we are able to check the PLC program. And the PLC programmer can start with the test. And only at that stage, it becomes clear whether everything is working smoothly or if issues occurs. And depending on the size and scope of the system, it is rare for a program to run flawlessly on the first try. So we have almost always adjustments to do, and depending on the complexity of the system, this can take a lot of time, like several days, to fix it. And yeah, most errors can be identified and resolved in advance by using the digital twin. And as a result, we can significantly have less real work on site, and this brings us benefits like faster commissioning and minimized downtime of the production, and shorter transition time between decommissioning the old system and starting the new system. And for our customer, that means they have better planning reliabilities. Here, this is a video, but it doesn't run. Oh, a little bit fast. Here, that should be a video. But that's live. Okay. Anyhow, this is a video. Imagine that is a video. So in this video, we usually show how we commission it virtual, or in a virtual commissioning, we do the commissioning of a system. There we have a robot, a Stäubli robot, and we have a PLC program. The robot is controlled by the Stäubli robotic suite, and the machine itself is controlled by a real PLC program. And this setup allows us to run individual PLC cycles. So we can test them separately separately and in combination with the robot. And that brings us to the situation that we are able to check if we have possibilities to optimize the cycles, and we can ensure that we have collision-free robot motion. And by the way, that was a project which was carried out during the COVID-19 pandemic. That was a time, I think that most of us knows that, where a lot of industries have problems with their supply chain, and parts have not been available. And in that case, it was the same way. We doesn't have the possibility to buy the parts, and or our customer doesn't got the parts, and so it wasn't able to have an on-site commissioning in a traditional way. So it was not feasible under these conditions, and yeah, there was the problem that it has a significantly delay of that project. And yeah, that's why we did some virtual commissioning, because then we have been able to prepare everything to start the machine once the physical parts and physical components were delivered and the system was assembled. In that moment, we was able to switch on the machine and nearly everything was working fine. Yes, after we have successfully commissioned the machine, we have done the virtual commissioning successfully, and all of our processes have been thoroughly tested, we come to the stage of the real commissioning. Now we can load the PLC program into the controller and we can start the physical system. And once the machine is running, we have a bidirectional connection between the real system and the PLC. That means the system sensors can send real signals to the PLC, which processes the information and sends control commands back to the machine. The simulation has not just a unidirectional connection to the PLC. That means the simulation only receives the signal from the PLC, and the simulation follows the real processes without influencing them. And at this point, we talk about a digital shadow, a visual representation of the actual state of live production. What could be a practical use case for that? In a customer's project, we continuously records and stores all information of machines and robots like axis values, joint positions, error messages, machine states, and we all save these information in a MES system. That is a system that runs like a database that documents the state of the entire production line at specific time points. And we can use these data sets and we can export them as a CSV file, for example, for a defined period. Then we import them into the simulation tool. And based on this information, we are able to have the entire system state, and we can visually reconstruct the whole situation that allows us to do some analysis and replication of error events. That means in a practical example, we have a machine unexpectedly shuts down during the night shift, and the next day we are able to read these stored data, and that allows us to trace exactly what happens and why. For example, direction. For example, we have a machine shut down because a conveyor belt have been overloaded. And that is because an HEV wasn't charged and was not able to pick up the produced parts from the conveyor. And this is something we can find out with our simulation, or we can find out that someone, maybe an employee, opens a safety door or something like this. This makes the traceability of error analysis significantly more efficient and helps to prevent similar downtimes in the future. Together with our customer Casto Maschinenbau, we implemented a digital shadow that simulates a complete warehouse system. The customer's tool, Casto Logic, is used as the central control system. And all changes made within this system can first be tested in the simulation before it will be transferred to the real system. And this allows employees to monitor in real time what the physical system is doing without having to be on the shop floor. And in this way, optimization potentials can be identified, processes can be improved, and decisions can be made based on the results of the digital model. And in the end, we are able to create a closed loop system where real systems, planning tools, and simulation tools are interconnected. The MES system transmits continuously live data from the production floor, and the digital shadow follows this information. And at the same time, the APS system provides information about upcoming production orders. And if we're using these data, we are able to do predictive analysis. So we can calculate the optimal time when, for example, an HEV should be recharged to ensure that once a task of a machine is completed, it has enough battery power to reliably transport the products to the next processing step. And yeah, maybe even this sounds like a future vision. This is already a state-of-the-art technology in our digital industry. So thank you for your attention. And now I'm happy to answer your questions you may have.
Thank you, Julius. I think this was a very interesting topic also for our audience, as we do have some questions for you. I would start with the first one. So how much time does it take to build a digital model? And what expertise is necessary, and how quickly can employees then get up to speed with the system?
Yeah, that is one of the most asked questions. And yeah, to give information about that, we say one thing is that we have around 4,000 parts in our e-catalog. That means we have machines, robots, and they can be clicked like by copy and paste, put them in the 3D world, and then we don't need to import CAD files. We have nearly everything in our database we delivered with us. And to create such a layout we have seen before depends on that how often you work with that, but it takes around 1 hour. Therefore, we give we support you as a customer. We give lessons, and that takes around 1 to 2 days, sometimes 3 days, depending how deep you want to go in. And yeah, so after that lesson, you are able to create such layouts we have seen before in around 1 to 2 hours.
Mm-hmm. Next question, what challenges can arise when implementing a digital twin, and how can they be overcome?
Mm-hmm. Yes, that is that thing is that after you set up everything, every part is placed in the situation at the position it has to be. It comes the biggest thing is that you need to you need to have the synchronization of the real time and the simulation time. That means like a robot, you want to pick up a 1 kilogram part. then he can move faster than combined with he want to pick up a 100 kilogram part. In that moment, the robot will move slower. And this synchronization is a little bit tricky, but in the end, therefore we have our project managers at Dualis, where we can support you with this kind of problems there.
Mm-hmm. Okay, so the next question is also into the direction of iTech. So I don't know if you're going to be able to answer it, but can we use the simulation tool to validate a new software update with the iTech test environment before deploying it on the iTech production environment? Can you say something about that?
Yes, depending on what you want to do exactly. If you have a firmware of like a CNC machine, in that moment, we cannot simulate that so deep. But if you want to have an update of an existing SPS program, a PLC program, or you want to improve the program of a robot, that is exactly what we're doing with simulations, because we can, after you set up the machine, you commissioned the machine, the process is not finished. You come to the point that you say, okay, we can improve it a little bit, and the improvements can be tested in the simulation. And so that is a possibility to validate software updates. Is that, I see Martin Heinz comes.
Yeah, maybe to step in shortly. Yes, you're totally right. But if you're talking about MES and MOM, then we talk often about processes, right? And I think the question is related as well to a kind of a process. And yes, indeed, we had already a project together with a customer simulating the whole line. So, and we were able as well into the integration phase to simulate as well the behavior of the line. And so we'll be able to have a kind of a test before we start really to integrate the whole system on customer side. So basically, we are looking forward as well to have such a kind of a, let me say, implementation and simulation as well as a given solution. So we are working already on that. So if there's a dedicated interest, please be so kind to connect to us, and then we have a short meeting about it and to explain a little bit more in detail. But basically, yes, it's as well possible.
All right.
Oh, thank you.
We have 2 more questions. I'm gonna go with the shorter one first, and then see if we have time for the second one. Where do you see the use of simulations in daily operations?
Yeah. To give another example, we have customers. They are companies. Let's say it in general. There are companies who do some welding. They have welding parts, and they are produced by robots. The welding Porsche needs to be driven by the robot, and sometimes they have parts they produce several times, like 3,000 times, and sometimes they have parts they just produce one time, and therefore they can test the robot program in the simulation. And this is something what they do every day. And every day they developing new robot programs, and because for new parts for new orders they have, and then you need to produce new parts, and then they need to have new robot programs. And in such situations, it is really helpful to have a simulation tool like Visual Components, because you can test it and find out if you have collisions, and it makes it easier to program or to edit the program. So there are possibilities to use it every day in the daily operations.
All right, thank you.